welcome Tony Green, and he's to talk about his 7 years at NASA.
Thank you very much. I would prefer you to save your applause for the end. But anyway, okay, you may have noticed this thing I put up on the screen before. Now, I preface my talk about my time in NASA with an explanation of the universe and where we fit into it. Now, some people find this contrary to their religious views. That's not my intention at all. My intention is just to portray scientific facts to you all and to answer whatever questions you ask me, hopefully. So I put that up there anyway. We'll switch that off for a moment. This photograph, which none of you can see, I'm sure, due to the black lighting, is a four-dimensional expression of the universe. The universe is spherical. The scientists postulate that there was a profound cosmic explosion, which they call the Big Bang, and from that everything else went out. Now it's very hard to see that. So what I've done is found this, which is, if you like, a kind of a trumpet right back to the start of time. If you can imagine this as a trumpet shape. This is the Big Bang, when everything purportedly started up again. And this is where we're at the moment, which is 14 billion years later, give or take a few million years. So that is the universe. It's been in existence, this current universe that we're in has been in existence that we know of for 13.8 billion years. And it's still expanding. And it's a very, very big place. Numbers don't really tell you the story. When we're talking about distances in the universe, even between ourselves and our own planets, we talk in terms of light seconds, light minutes, and light years. Now, what a light year is the distance that light travels in one calendar year. Now, light travels at 300,000 kilometres every second. So you multiply that by 60 to get minutes, multiply that by 60 to get hours, multiply that by 24 to get days, and multiply that by 365 and a quarter to get a calendar year, and you come up with a figure somewhere in the region of 14 trillion kilometres. Now, we can only see so far back into the universe, and that's because light has not yet had time, even travelling at an enormous rate, to come from some of the more remote areas to the Earth. It hasn't reached the Earth yet. So our scientists cannot observe it. So all that we can observe, we refer to as the observable universe. That's what we mean by the observable universe. And believe me, that's pretty big. So far we've managed to look back in time, because that light is travelling from way back when. We've managed to look at 90 million light years. 90 million light years, people. Each light year is 14 trillion kilometres. Do the maths yourself. You're very welcome. Yeah. So the universe is a pretty big place. The universe has not only got planets, stars, and other bits and pieces in it, it's also got what we refer to loosely as space. Now, space is not an airless, empty vacuum. Space is full of things like cosmic rays, small asteroids, photons, all kinds of garbage is in there, as well as two mysterious elements called dark matter and dark energy. Now, these things are purely theoretical at the moment. It's interesting how the scientists came up with this, though. The scientists estimated the mass in the observable universe, and it was too small. It was far too small. Given the amount of stars and planets and everything else they could see, there wasn't enough mass. So they postulated the existence of dark matter. Now this is a hypothetical thing, but by perfecting the maths, they came up with a model where if they added that to the mass of the observable universe, hey, they got the right answer. But it's still speculative, and it's still in a process of research. But where do we fit in? Good question. I'm very glad you asked that, young man. We occupy a very small galaxy called the Milky Way. And not only that, but we're right on the outer edges of that galaxy. On a fairly small planet by universe systems. But our planet's got water in a liquid state. Now the scientists will tell you that to have life, you must have water in a liquid state on the planet. This is debatable. Let's go with it for the moment. Okay, we're actually on a twin planet where there's the Earth and the Moon. The Moon is big enough to be regarded as a planetoid, a small planet. So really we're a twin planet system. The Moon revolves on its own axis and it revolves around the Earth, and the Earth revolves on its own axis. So we've got two systems going there. The Moon is the closest object in our cosmos that we can see, that we could even dream about going to. Now bear in mind, next February I'll be 80 years of age, and in my day at school, we used to work out how long it would take a train, a steam train on my dad, doing 60 miles an hour to go from here to the Moon. In the old money, the distance from here to the Moon is 250,000 miles. So that was my generation. And yet it was my generation who helped to put the men on the Moon. Not only that, but to put them down precisely where we said we were going to put them down and to bring them back. President Kennedy said, he gave us our dictum, our order. He said, by the end of the decade, you will put men on the Moon and you will bring them safely back to Earth. Now that was our total mission statement. And he had guys who worked out how long it would take a train to go to the Moon, doing it. Okay. The galaxy that we're in, it's very small by the size of other galaxies. And something you must have in your mind is that our planet is one of the 9 or 10 that we've so far discovered in our solar system. And our galaxy has got billions of similar planets in it, and there are trillions of other galaxies. For those of you who are not familiar with the mathematics, a billion is 1,000 million. A trillion is billion. So we're very small apples. In fact, if we disappeared tomorrow, the universe wouldn't give a rat's. It doesn't even know we're here. Okay. That's where you are. That is our galaxy. Right there. And we're right over there. In fact, if you were to come right up here and look, you can just see a very faint blur in the middle of that ring. We're very small apples, people. Yeah. Anyway, the thing is, we've got big ambitions, and we've got imagination, and we've got a fair-sized brain, and we know what space is now, we know what our neighbouring planets are, we've worked out our solar system, and we've figured out how far the nearest star system to us is. Why we've done that, I don't know, because the nearest star system to us is 4.37 million light years away. 4.37 light years away. Does anyone like to guess how long it would take in our fastest spaceship that we have today to get to that nearest star? Yes.
Zillion, billion, trillion, higher years, centuries.
So you're right, but I'd like a specific answer. Anyone like to put 160,000.
Yes.
That's how far away we are from the rest of the family, folks, so it's going to take us a while. But the Chinese people, whose culture I respect very, very heavily, have a saying, a beautiful saying. The longest journey starts with but a single step. And this, ladies and gentlemen, was the first single step on our way to the stars. It was going to the moon successfully and coming back successfully. Okay, well, as it says up here, 7 years on the NASA Apollo project. That's quite incorrect. It was 6.5 years, but 7 sounds a bit better. At the top of the thing there, you can see the front and the back of a medal. For every Apollo mission, and I was on Apollo 7 right the way through to and including the last one, Apollo 17. Each Apollo mission, hidden away inside the command module, they took a ball of beryllium metal. The sole purpose of that was when they returned, that beryllium ball was retrieved, and from that would cast the medals to the 80-odd thousand that were actually involved in the Apollo mission. So every medal I have has been into space and back, and that's as close as I've been, unfortunately. Right, the Apollo program, it started with Apollo 1, which was on the launch pad, doing what we call a countdown demonstration test, wet, which meant it was full of fuel, and there was a catastrophic accident on board. There was a spark, and I don't know whether you know, but our astronauts operated in a pure oxygen environment. Now you mix oxygen with a spark, and you get a very big bang. And those 3 men died within probably less than 2 seconds. 5. At that time, I was working in Britain in a British defence establishment, and we actually witnessed that. It was pretty dreadful, I'm here to tell you. Some years later, I got a phone call from a very nice American gentleman who wanted to meet up with me in a hotel in the town where I was living. So, you know, wanting anything better to do, I went. And he offered me a job with NASA. Whereupon I just cracked up, I just laughed. And I told him a joke. In those days, those of you who are a bit older can remember we were in the Cold War with the USSR, as it was then, the Russians. Now, the Russians had superb rockets, right? Fantastic rockets, taking off from the Urals. The Americans were having real problems at Cape Canaveral. So the joke was 2 almost identical rockets take off at exactly the same moment. One from the Urals, one from Cape Kennedy. Where do they meet? And the answer, of course, was Cape Kennedy. The Americans couldn't get off the ground. Now, I told this guy this joke, and he was not amused. The Americans were extraordinarily patriotic. And as a result of that, the interview terminated rather quickly. But about a week later, he called me back in, and he had a room about half this size set up with a movie projector, and he showed me the latest rocketry advances in the United States at Cape Canaveral, and the way that they were indeed launching their rockets. So I said, okay, I'll think about it. I was, a top dog in my game in Britain. I was getting good pay, and I was quite happy where I was. And then a month later, the wife had been on my neck about going to the seaside for a holiday. So I came in and I said, we're going to the seaside holiday. She said, where? I said, Australia. I'd been hired for the Carnarvon trucking station. We knew absolutely nothing about Carnarvon. We lived in a fairly select portion of Britain. It was 1968. We got to Carnarvon. I got off the plane in a 3-piece black suit, with a raincoat over my arm, and a very nice gentleman who was the PI guy for their tracking station, in shorts, thongs and a t-shirt, said, "I hope you missed the green, would you?" I said, "How do you know?" He said, "Oh, lucky guess." So we very quickly acclimatised, and as you can see by my presence, we're still here. But it was a culture shock. And that's a close-up of the medals. All of the medals are muscular muchness. Each one had the name of the astronauts, obviously, and each one had a sort of a little mission statement, if you like. They were his actual words, Neil Armstrong's actual words: "One small step for man, one giant leap for mankind." As you can see, I put the beryllium thing at the top there. I brought in 2 of my medals only, just so that you can actually see them. And we'll look at those later on. Now this was the Manned Space Flight Network, NSFN we used to call it. And bear in mind, ladies and gents, this is 1968, right? And this covered the entire world. Now bear in mind, we had no internet, we had no faxes even. We were at an extraordinarily primitive electronic level. We had teletype. That was the sort of top of the thing then. But there's an interesting thing about Carnarvon, little old Carnarvon down there. Here's Cape Kennedy. Now when you take a spacecraft off from there, it describes a kind of a sine wave like that. And guess where the first tracking station in the world is that it goes over after launch? You got it? Carnarvon. So we were called a prime site. And we were, without doubt, the best tracking station in the entire NASA network. When I was in the States on training, Americans would come up to me and say, "Are you the guy from CRO?" That was our call sign, CRO for Carnarvon. And I said, "Yeah, I'd like to shake your hand, sir." And that's the regard we were held in NASA. Now, this is quite true. I don't say this because I work there. This is absolutely true. So you should be very proud of that fact that it was an Australian tracking station that was the best in the entire NASA network. The way they worked out our reliability and our goodness or badness was the amount of data we lost on tracks of satellites and Apollo missions. I'm here to tell you that our catchment rate for data for many, many, many years was 100%. 100%. The nearest one to us was Bermuda, and they had something like 89%. At the end of the time, due to one incident, we were 99.59% data rate. And we were really cut up about losing that one track. And we were really, really cut up. No, we were. Even to this day, if we meet up, which we do fairly regularly, infrequently rather, it always comes up, "God, we lost that track." Yeah. Some of these things, you've got the ejection shift here. Now, its function was, when you take the spacecraft off from the moon, from the Earth to go to the moon, you don't go up and up to the moon. It would take far more fuel than we could ever get into a spaceship. And the spaceship would be so darn heavy you wouldn't be able to take off anyway. So what we do is we take off and go into orbit around our planet, the Earth. Right? Now, if you get a ball and then have a piece of string, when you start to do this, for a start it's down here, and as you go faster, it starts to pull out. This is the Coriolis effect, or centrifugal force, whatever you want to call it. So we spin around the Earth, and by doing so we gain enormous momentum, and then we inject into space. At that point, this ship is primed. The ejection point takes placed somewhere in space above that ship, and that ship can detect that. This is the same thing. We've come right around the world here. When we're coming back in, we've got two ships here. The reason for that is when you're coming back into the atmosphere is not consistent. For example, the air over the equator is about 5 times as dense as the air over the Arctic and Antarctic due to clouds and moisture in the air. So you would have what we call a footprint. It's sort of an oval shape like that. This is one end and that's the other. So we had two ships because we were never quite sure where in this area the people were going to land. Unlike the Russians, we could not land on ground. We just hadn't developed that technology. Okay. What did these tracking stations do? Very good question. I'm glad you asked me that. Yeah, thank you. Two things. One, we tracked the spacecraft. Now, by doing that, we sent out a radar signal that bounced off the spacecraft. We know the speed of light. I'll just explain that to you, 300,000 kilometres a second. So by working out the time that it's taken, we can work out the actual range, how far away it is. In Carnarvon, Bermuda, and Madrid, we have the most precise radar the world's ever seen. In fact, I don't think it's yet been surpassed. That's how good it was. It was called the FPQ-6. And when I first got to Carnarvon, my prime job was to take charge of that radar. That radar was so powerful that we could bounce a signal off the moon, receive it, and lock onto the moon. We could actually, the antennas would follow the moon for about 58, 59 seconds, maybe a minute. And you don't realise, but the moon actually revolves on its axis. You don't think so because you always see the same side. But it revolves exactly the same rate that we do. That's why we only see the one side. But it's revolving, and the Earth's revolving. And so you get this effect, it's called Doppler. This is like when you hear a train whistle coming towards you, you know, it sounds differently to when it's going away. That's sort of Doppler effect. But any radar in the world can only stand a certain amount of Doppler. Once it exceeds that amount, then it loses track. But that is how powerful that radar was, with many, many megawatts of power putting out, and we could track anything. At one stage, Bermuda, our sister station, actually tracked bees. They got a high altitude aircraft and they dropped a load of bees out of it, and Bermuda took track on them. The scientists then said, that's because of the wings on the bees. So a month later, up goes the same plane, drops a load of bees, who'd had their wings removed. And guess what? Bermuda tracked those bees. Yeah. We had a mission at one stage called Cannonball. Now, a cannonball is about that big, a sphere. And we tracked that and no sweat out of it. So we then had a follow-up mission called musket ball. Now, musket ball is half an inch, you know, 12 millimetres, about that big. And we tracked that too. This is 500 miles high in the sky. We're tracking a thing that big. This was some hell of a radar, I'll tell you. But anyway, after a while, the Americans specialise in everything. It's one of the drawbacks of being an American technician or engineer. They're very narrowly trained. British and Australian technicians are very broadly trained. I mean, I could equally well and have done fix the hydraulics that drive the antenna as equally easily as I could fix the very primitive computers we have. But we have people allocated to tasks in the radar, and one of them was our computer guy, and he left. And so I went to the American boss and said, look, I need a new computer guy. He said, why? I said, well, he's left. He said, well, you do. I said, I don't know squat about computers. He said, do it, get out. Now this is very American. It's not nasty, it's just the way they are. It's shape up or ship out with the Americans. As it happened, I did know a little bit about computers, and by the end of about a month I knew everything there was to know about computers. So what they do, they transferred me to the computer section, the main computer section of the whole tracking station, and I took charge of that. Then they sent me to the States, because I'd done a few clever things, and I worked very heavily hand in glove with Larry Novak, who was one of the head programmers at NASA, on a few very ticklish problems. One of them was, those a bit of physics will remember Newton's law. For every action there's an equal and opposite reaction. We tested that out, along with all the Einstein things we did and everything else, by an astronaut literally leaning out of an airlock of a spacecraft that was orbiting the moon and throwing out a couple of satellites. They were called PNSF. We call them Puffs the Magic Dragon. You know, it was quite a common pop song in those days, and we all loved it. So, now Puffs was good. When you're tracking something, you form a table called an ephemeris. What that does, it tells you exactly to the second when that satellite is going to come over your horizon and when it's going to go off the other end of the horizon. When it goes off the air, that's called loss of signal, LOS. Now we have our own little magazine, and when one of us dies, guess what? LOS. Yeah. There's a problem with the Puffs satellite. It was getting slower. Now there's no atmosphere around the moon. There's no atmosphere there, so what the hell was slowing it down? So Larry and I sat down for 3 whole days and 4 nights, I think it was, yeah. And I programmed a virtual tracking station on the moon. What you do when you're working out these ephemeris is you go to the centre of the planet and you work out from that with a simple XYZ Cartesian coordinates. So I pretended I was on the moon, and I put my little thing there. And Larry pretended that he was in a spacecraft orbiting the moon, and both of us tracked these satellites. That is how we found out what was happening. At certain points in their orbits around the moon, they were dipping down and then going back again. This, ladies and gentlemen, is how the mass concentrations that occur in 3 points on the moon, almost equidistant, like drive motors, were discovered. That's how we discovered them. So anyway, one function of the tracking station is to track the thing. The other, and probably the most important one, is there's a stream of data coming down from the spacecraft containing all of the essential information you need to know. Say Neil Armstrong's on there. What's his heart rate? What's his aspiration? His breathing. What's this? What's that? What's his blood pressure? Everything. You need to know that biomed data. You need to know, and you need to know it now, because on every Apollo spacecraft there was what we call triple redundancy. Any spacecraft, each spacecraft had a little computer. Very primitive, but it was a computer. If it failed, there was a backup one. If that failed, any tracking station on the Earth that was tracking that spacecraft could control it to the point of re-entry. We could actually make it re-enter. So that was triple redundancy. And we all felt really happy about that. Incidentally, that's why most of NASA resigned when they brought out the shuttle, because there was no triple redundancy loading on that shuttle, and none of us wanted to borrow it, so most people just walked away. But the biodata is the most essential thing, and this is where the computers were used. There's a lot of rubbish talked about the way the computers were used to fake moon missions and all this sort of thing. The computers were extraordinarily basic. My watch is something like 300 times more powerful in computing than any computer that we had in NASA. My phone, I really couldn't do the math on it. It is tens of thousands of times more powerful than any computer we had in NASA. My watch has got 128 meg of memory. That's 128 million bits of computer information. My phone has 16 gigabytes, 16,000 million computer words. Would anyone like to guess how big the biggest computer RAM was in NASA?
Were they 4 or 8 bit?
Hmm?
Were they 4 bit or 8 bit? Were they 4 bit or 8 bit?
30 bits. 30 bits. 30. Biggest computer we had in NASA had 32K of memory, 32,000. Technically that's not true. Technically there were two. We had one in Carnarvon and there was another one in Houston that had an extended memory unit, which the Americans called an EMU, and of course all the Australians called an EMU, which actually doubled up. We had 64K. 64K, people. That is nothing. That is nothing. So the computers were programmed by people like myself. One of my prime roles was programming. Have any of you seen that movie that's just come out called Figures, with the portraying the three African American lady mathematicians? Now, all that is true, but it's been very much Hollywood. Having done the tasks, many of the tasks that lady did myself, I'm about to show you the real computers that were used by NASA. Well, by those of us at NASA who were programming. This, ladies and gentlemen, what was used. And if you go and see that film Figures, when the lady's writing up on the chalkboard, that's pure Hollywood. What we did, we sat around usually in dark, damp corners with one of these little things, and we all had our own little books with formulae. I'm one of those people who can remember formulae, so I've got a very small book, but some people have big, thick reference books, and a slide rule, piece of paper and a pencil. And we would work out what the computer had to do, and then work out an algorithm that fitted into this very small amount of memory that we had to work with. So, in many ways, people like the African American ladies and myself were the true computers. And this is what amuses me when people say it was all faked on computers. And I said, well, would you like to talk to one of the computers? And they said, yeah. I said, well, you are. I'm one of the computers. Tell me how I faked it. And of course, we didn't fake anything. No, not one of us had anything really in our lives except for our reputation. And there's no way on this earth that any one of us would have jeopardised our reputations. In a technical world, your rep is everything. With a bad rep, you never get a job. You never get a good job. You might get a crappy one, but you never get a good one. Okay. So that was the Manned Space Flight Network. I've given you a little brief thing about what the tracking stations did. So we're getting into a bit of detail here. Carnarvon in 1968. I had a bumper sticker there. It said, George Kulisich, give me the trots. Because that's all you get. George Kulisich on the ABC giving out the trots. There's no TV, ABC radio only. the bitumen ran out of Manila going north, going south was Geraldton, going east on a dirt road, there was Gascoigne Junction, and the nearest place north was the Manila Roadhouse. We only had a primary school, no high school, so all the kids, once they reached high school age, had to go to Geraldton or Perth. Very few shops, we had one of each, but we had 4 pubs. We had a chemist called Mac the Quack. We had a dress shop called Anne's Frock Shop. And we had a drive-in theatre, and that was very, very popular. Very popular. But there's a peculiarity in Carnarvon that the visitors often used to remark on. There were no windscreen wipers on the cars in Carnarvon. And yet the windscreens were spotlessly clean. And the reason for that is that we kept them clean because we used to go to the drive-in. And we didn't have the thing, it never rained in Carnarvon for a start. And secondly, they got in your way when you were lounging back watching the movie, you know. Oh, it was a different world.
We're inside the car, Tony.
Around that time, 68, we bought our Boston 1800, 1967. 68, we went up to Carnarvon.
Yeah.
And around that time they had floods, which came from the
that was a little earlier.
it was the
That was 66.
They explained where the antenna was the part that was sticking out of the water.
Yes, yes. Yeah. The people who worked there, unfortunate thing was, in Australia at that stage, Australia was a little bit sort of behind, technically, particularly with the military. She was operating pretty old technology. So we were, in those days, leading edge. So they had to source people from leading edge countries, which in those days were the UK, Canada and the USA. But this, some magic worked once we all joined up. We all became Team NASA. I have never, before or since, experienced such teamwork. And the other thing that we had going for us is few, if any of us, recognised any technical limits whatsoever. I sat in a very posh hotel in Washington, D.C., and there was I won't tell you his name because you would know his name, a very brilliant scientist there who was trying to tell me that what we were trying to do was impossible. So I said, why is that? He said, well, what is the number of 2 raised to the power 29? So I told him. We knew these things, so that computers are binary, so, you know, it did a 0 or a 1, a binary system. So we all had the powers of 2 and 8. And he said, now, how many bits have you got on a computer with? I said, 30. He said, how are you going to track from here to the moon? I said, well, it's quite simple, really. We use 60 bits. He said, how the hell can you do that? You've only got 30. I said, we'll take one 30 bit, and we'll take a second 30 bit, and we'll add them together. It's called double precision. Dummy. I was pretty drunk at the time. These are the sort of solutions that we used to come up with. Up around the walls, where the ceiling met the wall, in most places we had little notices that said, there are no limits. And if you ever got into a sort of, where the hell do we go from here? Somebody would say, read the sign, man. And you'd look up and you'd say, yeah, that's right, if we get this, you know. And that's how we work. Now, again, due to the fact that there were very few females in the workforce at that stage who had the skills required. And the skills, believe me, were very peculiar. You needed to be a pure mathematician. You needed to be a physicist. You needed to be a troubleshooter. You needed to be a practical person. You needed to be a computer. I mean, the list went on. It was a very, very... People like me and the other guys there, we were pretty peculiar animals. So, the majority were male. There were a few females there, but they tended to be in jobs like in the teletype room, and of course, administration jobs, which were equally as important, but not as sort of glamorous, I suppose. That was the tracking station. It was a very big place. If you're driving from Geraldton there's a little road goes off down here called Memorial Drive now, into Carnarvon proper. Just before you get there, there's a gate, and that's all that's left, is a gate. There's no signage or anything. And I don't think there are any buildings left at all now. Now, one of my jobs when it ended was to take it to pieces. Some of the stuff we modified up to medical standard and donated to the local hospital. Most of the rest of the stuff went back to the United States, and some of the stuff is buried there. I could take it and show you where all the stuff is buried. Jupiter monitor, range and range rate area, SPAN. What does SPAN mean? Good question. SPAN means Solar Particle Alert Network. The problem with the old sun is that it sends out great gobs of energy on a fairly irregular basis. Now, if you're in a tin can in space and one of those bursts of energy goes over you, you're dead. There's no argument. We couldn't defend the astronauts against that. So we needed to know what the sun was doing at all times. So we had people there with a huge telescope, with a huge piece of blackened glass about this thick in front of it, so they could actually see the sun and watch what was happening on the surface. And of course we had an early TV camera there, and we put it on monitors as well. So we needed to know what the sun was doing all the time, because sometimes it could be a bit naughty.
So is that facility gone too, has it, Tony? Has that facility gone too? Has that sun spotting facility gone too?
The whole thing.
The whole lot's gone?
It's empty. That's where I initially went to work, at BQ6. Now, because we were so remote compared to the rest of the site, let me show you. This was the headquarters, right? So you can see we're remote from everyone else. They used to call us effing peculiar queer six personnel. You can make up your own word for the effing bit. And I guess we were in a way, but man, you know, we were tracking people going to the moon, and we were constantly fighting the equipment to keep it operational, and we were dedicated. You know, I know it sounds corny, but that's the only way I can put it, really. We had our own power station down here. Because we were using American power, all our equipment was US Navy, and so it was 115 volts, 60 hertz. So this was a little portion of America. We even had our own fire brigade. I was one of the firemen there, and we had an American fire engine which was 3 times bigger than the Carnarvon Town fire tender. They were very jealous, and ours was bright yellow, left-hand drive, 16 gears. Anyway, that was the tracking station layout. I know it's too much to take in altogether, so I'll show you some little parts of it. Now, how does this thing work, Frank? How do I...
You press the arrow, I suppose. What do you reckon, Roger? Not turning over anymore.
No, this is just going to track you to the south.
They're hyperlinks,
Huh?
They're hyperlinks.
Yeah, they're hyperlinks, yeah, but I want to know...
The button, just bring your thumb closer to you. Little arrows.
Oh, this one?
Yeah. That's it.
No.
Oh, sorry.
Good.
Yeah.
If I type a slideshow, you could make it do quickly.
What we need is a sign.
Yes. It would be the sign.
You sit there.
Yeah, you can do that.
Tony, what was the total staff on this operation?
185, around about there.
Not covering all the areas.
Yeah, yeah.
Your house there or house in general? Housing?
Yeah, we have the company provided asbestos.
In Carnarvon.
In Carnarvon, yeah. Okay, well this is the guy in the foreground with the white shirt is myself, the younger version of using.
Nerd.
Good 2 years old, isn't it? Yeah. And as you can see, everything was quite primitive and manual. So it was only when we were locked onto the target that our very rudimentary computer would then allow us to automatically follow the target. And as you can see, we've got a chart recorder. My mate, Georgie Allen, in the background there, he's watching the pens move on the chart recorder. These were primitive days, folks. Yeah.
An ashtray on the table too.
Eh?
You got an ashtray on the table.
Oh, yeah.
Well, he hasn't lost that.
Oh, we all smoke. I still smoke now. This is our antenna. Now, bear in mind, folks, we were tracking the moon with this antenna. It was only 10 metres across. Now, the beam from the radar was 1/2 of 1 degree. It's a very, very narrow beam. That Aboriginal bloke up there is actually me as well. That was pretty well how we dressed. There were no uniforms with Nauru. We had no real dress uniforms. And we dressed to suit the occasion. I'm dressed like that because I'm about to mess around with the hydraulics. And if you've ever got covered in hydraulic oil, you'll know that it's a waste of time having clothes on. Sorry about that, ladies, but it's true. It stinks. This was another small part of the tracking station where the data from the FBQ-6 radar was sent down to there so that these people would direct the big antennas down at the main building to start picking up the data that was coming down. They were called stay down. Now the TNC Centre was like the headquarters, if you like. It's the main building, the mission controllers were in there, the communications centre, unified S-band area, telemetry and the computer centre where I was working. The station director was there and we had things like admin and canteen and teletype room. That's it. Oh no, communications. We still used the telephone quite a bit. And we didn't have modems in those days. You see, we had DACOMs, digital to analog converters. And that went to mission control in the USA via the OTC station, which part of it is still there to this day in Carnarvon. And the Carnarvon people think that that was the NASA tracking station, but it wasn't. That was our communications link with the satellites. We used teletypes for normal messages and for hard copy. The data from the 2,000-foot magnetic tapes, that's the length of magnetic tape that was on the reel. Now you can see one here on the extreme left, and that's one of a nest of 4 of those things, and that was our main storage medium, the tapes. Now as the data was pouring in, it was interpreted by these computers in a way that it formatted the data. The data was then sent off through the DACOMs to OTC to go straight back to mission control, and at the same time it was recorded on those huge tapes. This was one of our more modern computers, the 1218. Oops. I'm sorry, I'm having a problem with this. Can't anyone see the cursor? Yeah. Oh, there it is, there it is, there it is. Yeah, we're getting it. This is our main computer room where I worked, and those computers there were the biggest computers in NASA. They were the Univac 642B computers. They weighed about a ton, and well, I've got a breakdown of one anyway, so I'll show you that. But that's a computer room. Those of you who are really observant will notice there's no keyboards and there's no monitor. So you wonder how we got the programs into the computers and how we knew what they were doing. I'll cover those answers in a little while.
So there's Univac in the hours. Is there ENIVAC as well? Was that ENIVAC? Was that another computer from back then?
We had RCA, Univac and Honeywell supplied the computers. Now I'm just going back momentarily back up to the FPQ-6 radar because it did have its own computer. If you can call it that. As you can see, it was a single tape recording thing, because really all we did was we tracked the object, and where our antenna was pointing was processed through our computer down to the main computers where it drove the USB antennas. We'll come to USB in a moment. And they were the antennas who were picking up the data. We at the radar did not pick up any data. We were like the, I don't know what you'd call us, but, you know, they did have a term for it.
Slaves.
Range finders, you know, we told them where to look, in effect, and we drove their antennas. As you can see, it's extraordinarily primitive. It's 4K memory, which was upgraded to 8K. 32-bit words on this one. So we divided it into two 16-bit groups, each containing 15 data bits and one parity bit. It's a bit of technical there for the geeks. But very, very basic computer. No graphics, no monitor. And the keyboard was a teletype. This is the main computer. And you can see it's got a massive 32 kilobytes, 30-bit memory. It worked at a blinding speed of 100 kilohertz. My watch works at 2.3 gigahertz. And my phone about the same. This thing weighed a ton. It took 3,500 watts of energy to run it. We needed chilled water to cool it. And it cost $400,000 in 1961. That's something like $40 million in today's money. But it was only a second generation computer, and it did have transistors in it, which were in those days quite an innovation.
Any breakdowns at all? Is it reliable?
Yes-ish. I was showing that for some reason nuns loved the tracking station. Now you've got to remember that the Vietnam War was on, and it was a common ploy apparently with American troops who were deserting to dress up as a nun to try and sneak back through the line to desert. So the nuns in those days were commonly called deserters because of that. But they loved the tracking station. And they used to come, and I remember our station director, who was a very proper person, explained to this group of nuns one time that the FPQ-6 radar is a bit like lying on your back on a dark night, looking at the stars through a straw. And what you could see through the straw is what the FPQ-6 was capable of doing, you know, that sort of thing. Oh. But I had this group of nuns come into the computer centre one day, and as the team leader down there, one of my jobs was to show visitors around. We obviously did not let them in completely in. We brought them just inside so they could see everything, and my job was to explain what was going on. In the process, I looked over at one of the 642Bs, and it had an error code showing on the lights that were illustrating what was happening in the register. And I said, "You got a 717? To one of my guys, and he says, "Oh, okay," and he got on it. And I'm talking away to the nuns, and this head nun lady, she said to me, "Can I go really close to that computer?" I said, "Well, for what purpose?" She said, "I just want to look." I said, "Yeah, sure." And she went right, and she was, an inch away from these little red lights. And I said, "Can I ask you what you're looking for?" She said, where did you read those numbers? But of course, we were reading them in binary coded decimal. The lights were arranged in groups of 3, and we were, you know, oh man, yeah. Quite funny, really. That was the 1218. For its day, it wasn't a bad little computer actually. Quite reliable-ish. Oh, we've done that. We'll go back. But they were the really cruddy computers. They really weren't very good at all. And they were only used for just shoving data through. There was no graphics capability on them at all. So this business of faking it through the computers is a complete furphy. That was the Solar Particle Alert Network with Staydown in the background. There were really peculiar people who worked at SPAN. You imagine sitting there all day looking at the sun. I don't know if any of you have had the opportunity to see photographs of the sun. It's a very obscene looking object. It's really not nice. You know, I've seen better things crawl out of a barrel, you know, than the surface of the sun. But nevertheless, they were an essential part of the safety of the mission, and so, you know.
So there was a consistency, was there, with those bursts from the sun?
No.
So you could...
No, the only consistent thing about the sun is that it... oh, goodness.
Keeps changing.
It has an 11-year cycle, and once every 11 years, the sun's poles actually reverse. The sun has done a complete turnaround like that over an 11-year period. Now that's the only consistent thing about the sun. Everything else is day to day. So, you know, and it's no good putting a brown paper bag over your head either, because it doesn't work. If you're in a spaceship with cosmic rays pouring through you. Ah, got it. Now look, behave yourself. You've got to talk to these computers. That was the Unified S-band. As you can see, it's called USB, which has now got a totally different connotation. I will go down to the facts thing to show you why it was called that, if I can find the pointer again. You must give me the manufacturer of this computer, Frank. I will put it on my list of computers I will never buy. There it is, yeah. You've got to remember, we had very primitive gear, and we had to make do with everything. We had to try and make everything do at least 2 or 3 things. So this is what we did with the Unified S-band. Remember what I said about the bio data? That was the most important data that was coming down from the spacecraft. Never mind about the range and exactly where it was. We needed to know that at certain times during the mission, but at all times during the mission we needed to know the health of the astronauts. So what we did with this is we combined or unified all these things together. Voice communications, television, I'll come back to that, telemetry command, tracking and ranging into one single system to save size and weight and to simplify operations. The computers that we had weren't capable of processing all of those things independently and then combining the end result. They just were not capable of doing that. So we had to do it with hardware, and that's indeed what we did do. So that's pretty well everything about the tracking station. We have a saying, those of us that are still left, to keep the dream alive. And the way we do that is by doing what I'm doing right now, which is talking to anybody and everybody who's got the slightest interest in what we do. And most of my work has been going around the schools, talking to young fellows like this, because they are the ones who colonised Mars. They're the ones who colonise the rest of the solar system, and they're our future astronauts, hopefully. And those of us that were involved, even at the minute level that we were involved, this was our dream. Right? This was our dream. At home, I've got a plaque this big, which is an exact replica of the plaque that's on the lunar lander that first landed on the moon. On that plaque, it says, "We came in peace for all mankind." And pretty well, that's where we were coming from. It was this pure peace and science exploration. We weren't concerned about getting new real estate or anything like that. We just wanted to go there and just leave footprints and come away. Unfortunately, we had to leave the bottom part of the spacecraft because we needed something for it to take off from. Finally, I'll just say that takeoff from the moon was by far and away the only time during an entire mission when we all held our breath. That was the most dangerous part of any Apollo mission. The reason is that, again, due to, we just could not afford mass. We had a saying, 1 pound of weight is 10 gallons of fuel. In other words, if you carried an extra pound of weight, you needed 10 more gallons in your spaceship tank to take off. Now, bear in mind, we did all this with imperial measurements. There were no metric measurements when we went to the moon. And we had an accuracy with our radar guidance of 1 inch, 2.54 centimetres from here to the moon. That's 256,000 miles in the old money, 400,000 k's in the new money. That's pretty good going for 1968, 1972.
How much fuel did you put into it? How much fuel did it take to get there and back?
This lander had enough fuel to land. And when Armstrong was the pilot on this mission. Buzz Aldrin was the captain, but Aldrin was the pilot. So when he took manual command of this, which he had to do because they were going to land in a crater, he immediately assumed authority for the mission. By the time he landed, he had something like a cup full of fuel there. Because we were really, really worried about that. You see, at that stage, we didn't even know what the moon was made of. A lot of scientists have told us it was suicidal to go there because there'd be at least 10 feet of talc. Now, you can't land anything on talc, you know. But going back to this dangerous bit, all there was in there was a rocket, a very simple rocket, almost like the blue touch paper in retirement. And it was what we call a one-hit rocket. If that didn't fire, those 3 guys were dead because we had no way of getting them back from the moon. And every time we put them down on the moon, that little rocket fired and separated the upper portion here, the wider portion, from the base, which acted as a takeoff point every time. Now, on the very final mission, there was a camera left sort of like here, and I actually met the guy who controlled that camera on Earth. It takes 2.5 seconds for a radio signal to go to the moon and come back. Now, this guy trained for something like 18 months with a 2.5 second delay. In other words, he would do something 2.5 seconds before it was required. Okay, you think about that. That's a pretty hairy thing, because you're doing something and there's no return for ages, you know. And he actually filmed the takeoff. It's the first time we'd ever filmed the takeoff from the moon's surface. We'd filmed it from the CSM, that was circling above, but not from the moon's surface. And it went up and up and up. We were all cheered, we all thought it was great, you know. Then he lost it. And then he found it. None of us could believe it. This guy was so skillful, he actually went to a position and actually caught it again and followed it up. If you ever get a chance to watch that video, just think of that poor guy sitting in a room doing something 2.5 seconds before it's required, you know. Anyway, that's pretty much it. As I said, we didn't have a uniform. All I got is a goddamn hat.
So with this time lag that you're talking about, Tony, there must have been a lot of guesswork, anticipation, because you know you're sending an instruction and it's not getting there. Do you what?
You don't do guesswork when guys' lives are on the line.
No, they were my words, but you know what I'm saying is that you know, okay, you're giving an instruction, but you're giving it, and they're getting it later. Yeah. Right. I mean. That must make a lot of difference to what's happening.
We prepared for that. We knew that when they got to a certain point, there would be a time delay of, let's say, 1 second. So we would send the command
earlier, so they'd get the right.
So that the command got there at exactly the right time that was needed to change their orbit or whatever we needed to do. Yeah, that's right.
One just a question I've got. I don't want to get particularly technical the answer, but I understand that satellites that are orbiting the Earth, say the GPS coordinates, they have to reset the clocks on the satellite every day because the time passes, there's no effect on. Did you perhaps
you're into Einstein's theory of relativity now. And yes, that effect is noticeable, but only over a very long period of time. What we did with NASA one time, we took an aircraft with a cesium clock in it, and it was identical to a cesium clock that was on Earth. And we flew the aircraft clockwise around the Earth, and then saw the difference between the airplane clock and the ground clock. And there was a difference, exactly to Einstein's prediction. So we then flew the airplane around the other way, and again it worked out to Einstein's theory of relativity. So his math was right, you know.
It's like it's about a whole maintenance that take that into consideration if you are looking for things and things like that, and timing, and if they've got their own board computers and you've got your computers on Earth,
Yeah.
that must add a lot of complexity as well.
Well, no, because the two are talking,
Okay,
and what you do, you sync. You know, everything's synced. So wherever the master sync is, let's say it's on Earth 3, that dominates. Yeah. It's the same way that you watch and your computer and your phone keep perfect time.
Yeah.
There's somebody syncing you all the time. But the bigger problem is in the three-dimensional aspects of everything when you're dealing with the moon. And I've already mentioned time variations. For example, do you know what the theory, how to work out the volume of a hypersphere? Do you know what a hypersphere is? A hypersphere is a four-dimensional sphere. It's a fifth dimension expression. The volume is 8 times pi squared times r raised to the fifth divided by 15. Now, you try working that out on the sideboard, man. Or on a computer without a keyboard. And as the gentleman over there detected, it was all machine code. So I had to write in exactly the same language that the computer was working in. There was no, not even basic or PL1 was the first language that came out. Not even that.
Yeah. A lot of the early computers used machine code anyway, purely for speed.
Yeah.
If they had a sexter that they wanted fast, machine code, then they bring it forward.
But fast is a relative term. The fastest computer we have at 100k clock. That ain't fast. Believe me. I'm faster on the slide, and we quite often work. Yeah, you know, in fact we used to call ourselves the human computers, you know. Yeah. No, it's the physics involved sounds very complicated, but it's not. In actual fact, the physics involved is relatively simple in that you've only got a certain number of things that you've got to consider. I mean, if you were going from here to Mars, it would pretty well be the same mathematics that we used to get from here to the Moon. But if you were going from here to Alpha Centauri, then we have to start looking at other factors. Time becomes a predominant factor in those sort of things. Time's a real nuisance. You can never find a way to move it.
Tony, you mentioned the sun
Yeah.
and changing polarity.
Yes.
Does that have much effect on travel?
On
Travel? Space
Uh,
travel?
strangely enough, it does and it doesn't. The Concorde, one of the main reasons that they never brought back another Concorde is because it flew too high and it was up right up in the stratosphere, and that was getting impacted by the solar emissions in not a very good way. Interestingly, I don't know if you know that, but the Concorde actually stretched 14 feet long when it was at maximum altitude, maximum speed. So again, you're into relativity stuff there, you know. Yeah. But if we stay in our atmosphere, in the dense part of our atmosphere, we're pretty safe from the sun. The big indication, as the young fellows just told me, is at the poles. The aurora borealis and the Antarctic one. The Australis, thank you. The south, and then Atlantic and Australis. Yeah. The aurora australis start to come up enormously when there's a lot of solar power bashing it. It's a very complex algorithm. You've got the Earth like that, you've got the sun here, pushing, if you can imagine like wind, so you've got an effect around the earth like that, and turbulence, and all kinds of pretty heavy duty mathematics. But the earth is shielded by its magnetic field from a lot of solar flares, and that manifests with the lights, the northern and southern lights.
Tony, you were saying that one of the main things you were doing is monitoring the vital signs of the astronauts. Was there a degree of difference closer to Earth, further to the moon? Whether
You
noticeable differences in their vital signs and that sort of
These people were superbly trained and superbly confident in their job, and that makes a hell of a difference. I mean, you couldn't compare yourself or myself with any astronaut. For example, Apollo 13, which I still maintain was our finest hour, when we managed to get those guys with a crippled spacecraft around the moon and back, and got them back to Earth safely. There was a problem, however, when they were getting back closer to the Earth. They were starting to run out of things in a big way, and one of them started to exhibit signs of distress. Now, his heartbeat was well over 200. Now, that would have killed any one of us in this room probably, in a matter of seconds. He survived. And this is a measure of the immense physical and mental training these people have had, and their actual condition. It's far different to the rest of those near mortals, I'm afraid. Yeah, but we had to check that all the time. The main reason was, well, the two reasons. One, to check that the astronaut was okay, and the other one was that if he wasn't okay, we had to know why, which usually meant an equipment malfunction. They had a very primitive comms, biodata was the main thing that we looked at. It was from that all else could be worked out.
Do you think part of the theory of, or the non-belief might have been in that very fact that these chaps were so trained that they almost had a monotone in the way they spoke? They didn't get excited like we would. Oh my God, look, we're off the Earth. And then, and it was coming back like robotic almost.
Yes.
So some people might have thought that was unusual.
Yes. Yeah, well, I've met 2 or 3 of the astronauts. I think that Armstrong, but he was a bit different to the other astronauts. I don't know, he's different there. John Glenn, people like that I met, and they were not normal people. They were highly trained professionals. I don't really know how to describe it. Much different to other mortals is probably the best way I can put it. Right. This is set a record today, folks. This is the first time I've ever given this lecture and people haven't asked me about aliens.